Warmup, greedy and randomized greedy algorithms. In this section, for simplicity, we will assume that all losses are either 0 or 1 rather than a real number in the closed interval between 0 and 1, which will simplify notation and proofs, although everything presented can be easily extended to the general case. Our first attempt to develop a good regret minimization algorithm will be to consider the greedy algorithm. Recall that Li to the t equals to the summations of Li to the tau, summation summing with the tau starting from 1 to t, namely the cumulative loss up to time t of action I. The greedy algorithm at each time t selects action x to the t equals to the argument minima chosen between Li to t minus 1 with index I in x. If there are multiple actions with the same cumulative loss, it prefers the action with the lowest index. Formally, greedy algorithm initially set x to the 1 equals to 1. At time t, let L mean to the t minus 1 equals to the minima of Li to the t minus 1. The minima is set for is chosen between the I in x and s to the t minus 1 equals to the set of I such that Li to the t minus 1 equals to L mean to the t minus 1. And let x to the t equals to the minima of s to the t minus 1. Theorem 4.2, the greedy algorithm for any sequence of losses has L greedy to the t, which is less than or equals to n times L mean to the t plus n minus 1. Proof at each time t such that greedy incurs a loss of 1 and L mean to the t does not increase. At least one action is removed from s to the t. This can occur at most n times before L mean to the t increases by 1. Therefore, greedy incurs loss at most n between successive increments in L mean to the t. More formally, this shows inductively that L greedy to the t is less than or equals to n minus the size of x to the t plus n times L mean to the t. The above guarantee on greedy is quite weak, stating only that its loss is at most a factor of n larger than the loss of the best action. The following theorem shows that this weakness is shared by any deterministic online algorithm. A deterministic algorithm concentrates its entire weight on a single action at each time step. Theorem 4.3. For any deterministic algorithm D, there exists a loss sequence for which L d to the t equals to t and L mean to the t equals to the flow function of t over n. Note that the above theorem implies that L d to the t is greater than or equals to n times L mean to the t plus t mod n, which almost matches the upper bound for greedy. Theorem 4.2. Prove fixed a deterministic online algorithm D and let x to the t be the action it selects at time t. We will generate the loss sequence in the following way. At time t, let the loss of x to the t be 1 and the loss of any other action to be 0. This ensures that d incurs loss 1 at each time step, so L d to the t equals to t. Since there are n different actions, there is some action that algorithm D has selected at most the flow function of t over n times. By construction, only the actions selected by D ever have a loss. So this implies that L mean to the t is less than or equals to the flow function of t over n. Theorem 4.3 motivates considering randomized algorithms. In particular, one weakness of the greedy algorithm was that it had a deterministic tiebreaker. One can hope that if the online algorithm splits its weight between all the currently best actions, better performance could be achieved. Specifically, let randomized greedy RG be the procedure that assigns a uniform distribution over all those actions with a minimal total loss so far. We now will show that this action achieves a significant performance improvement. Its loss is at most an big O of log n factor from the best action, rather than big O of n. This is similar to the analysis of the randomized marking algorithm in a competitive analysis. Randomized greedy RG algorithm. Initially, pi to the 1 equals to 1 over n for I in x. At time t, let L mean to the t minus 1 equals to the minima of Li to the t minus 1, where the minima is selected between the index I in x and s to the t minus 1 equals to the set of I such that Li to the t minus 1 equals to L mean to the t minus 1. Let bi to the t equals to 1 over the size of s to the t minus 1 for I in s to the t minus 1, and pi to the t equals to 0 otherwise. Theorem 4.4. The randomized greedy RG algorithm for any loss sequence has LRG to the t is less than or equals to ln n plus 1 plus ln n, and the sum of 1 plus ln n times L mean to the t. Proof. The proof follows from showing that the loss incurred by randomized greedy between successive increases in L mean to the t is at most 1 plus ln n. Specifically, let Tj denote the time step at which L mean to the t first reaches a loss of j. So we are interested in the loss of a randomized greedy between time steps Tj and Tj plus 1. At time any t, we have 1 less than equals to the size of s to the t less than equals to n. And furthermore, if at time t in the half open interval, with the open interval on the left hand side Tj and a closed interval on the right hand side Tj plus 1, if we at time t chosen between such an interval, the size of s to the t shrinks by k from some size n prime down to n prime minus k, then the loss of the online algorithm RG is k over n prime, since each such action has weight 1 over n prime. Finally, notice that we can upper bound k over n prime by 1 over n prime plus 1 over n prime minus 1 plus blah 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 plus 1 over n prime minus k plus 1. Therefore, over the entire time interval, Tj and Tj plus 1, the loss of randomized greedy is at most 1 over n plus 1 over n minus 1 plus 1 over n minus 2 plus until 1 over 1, which is less than equals to 1 plus ln n. More formally, this shows inductively that LRG to the t is less than equals to 1 over n plus 1 over n minus 1 plus blah 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 until plus 1 over the size of s to the t plus 1 plus 1 plus ln n times L mean to the t.